Welcome. In this video I'm going to show you how you can determine measures of qualitative variation using R. Um, and I'm using Jupyter Lab, but all this code should also work in RStudio, for example. The packages that are installed by default are these. And I'm just going to show you a little bit about how these can be calculated, not so much into details on what they actually mean and which one you should use. The problem is that there is a lot of different ones. I try to group many of them together, like many are based on the mode, a few are based on the average number of frequencies, some are based on something known as entropy, and some deal with evenness, and there are a few that I couldn't really place. Now, to show you how this works, I'll first load in some example data. GSS is General Social Survey from 2012. And then I'm going to be using the marital status as the example. So just to have a quick look at the counts, here is using the table function, and it shows that, for example, 314 people selected divorced. Now, there are a few things that we might need all the time, which is the number of categories, which can easily be done with length, and sum as in the number, the total sum of cases. So in this case, there were 1941 people who answered this question. Now I have my own library that actually has just one function that can calculate all of them. But this video is about not using those, so I categorize them a little bit, or at least I try to. So mode-based measures, they look of course at what the mode is, or at least the frequency of the mode, which in this case is 972. You then have the variation ratio, which is simply 1 minus the proportion that's actually in the mode. So that's almost 50% is not in the model category. There's the Berger-Parker index, which is even simpler. It's the percentage that is actually in the mode, so 50% almost was in the model category. There's the variation ratio, slightly modified by Wilcox, so that gives this value, or if you like the alternative formula, there are two as you can see, but they each give the same result. So it's most often just following the formula along. Same thing here. We need the minimum value, so we can simply use min, and this gives then the range variation ratio from Wilcox. Then there are a few that are based on the mean, so they basically average out the frequencies, which should be simply the sum of the frequencies, so the number of cases divided by the number of categories. Now Wilcox does average deviation for this, so we can simply, it looks scary this formula, but you can simply do the sum, that's the big E value, of the absolute values, those are those stripes, and then subtract the mean from each frequency and divide it by this one, 2 times the average times the number of categories minus 1. So we actually have everything already, and the alternative formula gives the same result. Gibson-Poston M4, again nothing new here, summation and absolute sign, so we can simply follow the formula and get the result. Gibbs-Poston M5, same thing, nothing to worry about. It looks always a little bit scary, but most of the values we already have, and they're actually simple functions like sum and absolute values. So here this is also fairly straightforward. This one has different names, but they all come up with the same result. And here is another M2, different formula, same result. So here we go, and again the same result. Then we have the standard deviation version. It uses a square root and a square, but square root is available with the power of a half, and we can actually simply calculate this one. It seems like I've forgotten actually the power of a half there. It's doing that minus that squared plus times 1 squared, so it should actually have an additional times 0.5 there, so it's slightly less. Alright, so that's fixed now. The entropy based, these often use the percentage, so they look at percentages instead of the counts. The most common one is the Shannon or Shannon-Weaver entropy. It takes the log ln, is simply the natural logarithm, which is available in R using log. The Renyi uses logarithm base 2, which is available as log 2 from R, so we can simply follow that one along. It's just a lot of them. Here we have to, again, log 2, so nothing new. We can simply use that one. And the Sheldon index is using the Euler to the power, Euler number to the power of something, so that's exp available in R. The hype index, the same thing, nothing new, using the Euler number. Last but not least, the diversity and evenness, besides the two additional one. This is a little bit trickier. Here we have, depending on what A is, if it's unequal to 1, we do this, and otherwise we do this. So we can do that in R simply by doing an if. So if that alpha, which you can set to whatever you want, equals 1, then it's simply the HSW. And otherwise it's the sum of the proportions to the power of that alpha, and all of that then after it's summed up to the power of 1 over 1 minus that alpha. And I think that's about it. So we can simply do that one. For an evenness hill, it defines actually both by 2, so you do the same function twice, but then for 2 different values. Boola E is nothing too scary. There's a big sum here, and then of the minimum of the proportion are 1 over k, whichever is smaller. And then this is just one big fraction with some small fractions in the numerator and denominator. And it turns out to be 0.62 again. Multiply this with the number of categories, and you get the diversity score. Simpson D, nothing fancy here. It's just using the frequencies, so we can simply calculate that to be 0.33. We can also square the proportions. That's a slightly different one, and you get the same result. If you want the dominance score rather than the evenness score, or then you can simply subtract them from 1, so that's sometimes done, and sometimes we use the squared values of the proportions and subtract the sum of those from 1. M3 looks scary, but it's just minimums and sums, so we can simply fill out the formula. The same thing here, so all of them, again, the natural logarithm is just the log function in R. Smith-Wilson E3, nothing too strange. We can use the D2, the Simpson value again, multiplied with K. And last but not least, the 2 that I couldn't really classify anywhere. This sums twice, so we loop over all the categories and then loop over them again. So it actually is doing all possible combinations, all possible differences, and then the absolute values of those. And we get 0.48. Kaiser B is even scarier looking. We have a big square root again. So that's to the power of a half. Inside is 1 minus, so here's your 1 minus. And then this big looking pi is actually the product operator, so it's similar like that big sigma, this one, but instead of here you add every time, here you multiply every time. So that's what product is for. And you might notice it's the square root, but not just the square root, it's actually the kth root, which is the same as doing to the power of over, to the power of 1 over k. And that gives us the last one, and that's there. So that's a lot of different measures of qualitative variation. Alright, I hope this was somewhat helpful. It's a long video because I had to go over all of them, but I still hope it was helpful. All right, thank you for watching, and um, if please like and subscribe, etc. All right, cheers.